Thank you for coming to my talk. I'm just going to get right into it. Materials that can convert light into an electrical current are of immense interest for a variety of potential applications, in particular optical detectors and power generation. And one material that's been theorized to produce this kind of photocurrent response is MOT2, molybdenum ditelluride. My name is Marissa Romanelli. I'm a rising junior and physics major here at Boston College, and I work in the Birch Lab where I study MOT2. So today I'm going to talk about how I fabricate devices for MOT2, basically how I go from a piece of crystal to something with electrical contacts attached that I can use to make electrical measurements and to see what this photocurrent response looks like. So a brief outline of my talk. First I'm going to talk about why I'm interested in MOT2 in the first place. And the short answer to that is it lies at the intersection of beneficial potential applications and also some opportunities to learn things from a fundamental physics perspective. I'm going to talk about ways that similar devices are fabricated currently, which is often done by fabricating in a clean room. I'm going to talk about the methods we use in the Birch Lab and how I can use something as simple as a piece of tape to produce a usable piece of crystal. I'm going to continue and talk about the devices that I've made this summer, including this one, and how I've worked to improve the fabrication process. And finally, I'm going to talk about my future research plans in this area and how we're going to go about actually measuring the photocurrent response. So when it comes to why MOT2, there are really two main reasons that it's interesting to study. One of the first one, as I've mentioned before, is the potential applications. So optical detectors, we're going to study the photocurrent response in the mid-infrared, which is useful for thermal imaging, and also because organic molecules have a lot of vibrational modes in this area, so potential biochemistry applications. And of course, turning light into electricity is also a potential source of power. And usually, when you want to convert light into electricity, you're converting what's essentially an AC, alternating current electric field, because light's a wave, it oscillates, into a DC current. So usually, the way this is accomplished is by having some material where you've separated some charges, positive on one side, negative on the other. So you've got an electric field in your material, and when your light shines on it and you generate a negative charge and a space without a negative charge, which you could think of as sort of a positive charge, they are attracted by the electric field and they separate, and that produces a current. However, in addition to this, to the challenges of fabricating something like this, the electrons can also scatter somewhere else in the material, which means your current gets lost and your light wasn't converted to anything. So there's sort of a cap on how efficient a device like this can be. MOT2 doesn't work by this mechanism. It actually has its own intrinsic response, which directly converts an AC current, an AC electric field into a DC current, which has the potential to make it more efficient as far as the application side, but is also interesting from a physics perspective, because this coefficient, this sigma here, is actually related to how the electron wave function evolves in the material. So the wave function is basically an equation that kind of describes everything about the electron, and so learning about how it changes throughout the material tells you about how your electrons behave in the MOT2. Normally these wave functions are measured sort of indirectly, but this would enable us to measure directly how it evolves. This is like the difference between seeing bare tracks and seeing the bare. But in order to fabricate a device that can do this, there are a couple major limitations to how you have to work. One of these is that the contacts must be clean, which in other words, there can't be any sort of organic material between the piece of crystal that you're trying to measure and the contacts you're attaching to it. So this is usually accomplished by fabricating in a clean room, so going down to some other facility where there's no dust or contamination of any kind, and then you fabricate contacts there. You also have to make sure that your sample is very thin, because when you shine light on your material in order to measure this response, the light only penetrates so far into your material. And if you've got all this extra material on the bottom, the electrons of the current that you're making can scatter down there, and then you don't measure that as part of your response. So usually, in order to make a thin sample, thin films are made using molecular beam epitaxy, which is what this big expensive looking machine over there is. So a lot of times materials are fabricated by directly growing a thin film. Neither of these two methods do anything to address air-sensitive materials like MOTE2. No matter how clean your clean room is, there's still going to be oxygen in there, obviously. And so an air-sensitive material like MOTE2 will degrade as you're taking your measurements, and you won't be able to get as accurate of a measurement of its response. So in order to solve sort of the challenges of cleanliness and air sensitivity, in the Birch lab, we do all our fabrication inside this lovely glove box. So it's full of an argon atmosphere, which is inert, and contains almost no oxygen, levels as low as 0.1 parts per million. So I can do the entire fabrication process, make an entire device without my MOTE2 ever seeing air. So that solves the challenge of cleanliness and the challenge of air sensitivity, but it does nothing to address thinness. And obviously, as you can see, you wouldn't be able to fit a thin film growing machine inside this glove box. So actually, the answer to making a thin piece of crystal is this technique called exfoliation. So MOTE2, which is the structure you can see up on the left there, is a van der Waals bonded crystal. So you can sort of imagine it as like a stack of sheets of paper. So the bonds within each layer are strong, but the bonds between the layers are rather weak. So weak, in fact, that I can take an ordinary piece of tape, peel off a few layers of crystal, and slap them down on a substrate to make a flake like this, which can be as thin as, so far, we've gotten it down to 20 or 30 nanometers. So now that I've got my flake, right, I'm just going to slap some wires on it and call it a day. Absolutely. Yes? Never mind. Even assuming that I could have a wire 200 microns across, about twice as thick as the average human hair, you can see from the size of this circle compared to my flake that it's like an order of magnitude bigger. So if I want to attach contacts to this flake, I'm going to need a different method in order to connect it electrically. And that method is called photolithography, which is basically writing with light. So, if I want to write a pattern for my contacts with light, I'm going to need to start by putting on some light-sensitive chemicals. And when UV light is shined on these chemicals, this photoresist, it makes them soluble in a developer, so I can dissolve away that area where I want my contacts to be. Then I can thermally deposit gold all over my substrate. I can put this in a different chemical that dissolves away the rest of the photoresist. The gold I don't want floats away, and I'm left with some contacts that can start as my flake and head out to some big wide square that I can actually stick a wire to now. Finally, since our measurement systems are outside of the glove box, I need to do something to protect my device from air when I take it out. So I transfer a flake of HBN on top of my device to protect it from any air getting in. Since HBN is transparent in the wavelengths we want to use, and it's an insulator, it's not going to affect our optical or electrical measurements, but it will keep the air out of my sample, so I don't have to worry about that. So this is sort of what that looks like in real life. Here's the first device that I made this summer, and if everything goes well, I can make one of these devices in about a week. It takes a couple days to find a good flake because they're small compared to the chips we're searching on, even on a 1 centimeter by 1 centimeter chip, which doesn't seem that big. Finding a flake like this is kind of like looking for a penny in a football field. And then after that, it goes on to the process I just described through the photolithography and the transfer, which takes a couple days, assuming nothing goes wrong, and then it can go on to measurement. So before we even measure the photocurrent response, we want to find out the resistance of our device, sort of to see, what kind of response do we expect, like how strong should it be, what kind of laser power can we use on our device without damaging it. So what we expect to see is that our device should act like a resistor. So if you're familiar with Ohm's law, V equals IR, anyone who's taken intro physics, as we change the current and measure the voltage that comes out, it should make sort of a line where the slope is the resistance, and it should be, quite linear. But what we saw when we put this device in and measured its resistance is we saw that it actually made a curve. Our device is acting like a diode. It's more resistive when the current goes one way than goes the other. So what this suggested to me is that our fabrication process is not as perfect as we thought it was. There must be some sort of impurity between the flake and the contacts. And the problem is that what we assumed that when we were doing this photolithography step, when we developed a way the spots that we had shown UV light on, we assumed that all the photoresist went away, it's perfect, it's all gone, no issues. In reality, what probably happened is that not all the photoresist dissolves, and there's some left between the contacts in my sample. So I need another way to ensure that all this leftover photoresist has been taken off. And so what I decided to do is to clean the contacts with an argon plasma. So since it's hot and it's ionized, argon plasma is good at removing these organic molecules that the photoresist is made of. It just sort of breaks the bonds and makes them come right off the surface. So I'm actually in the process of making a device to test how well the argon plasma worked. We've already argon plasmid it. I'm working on transferring HBN onto it now so I can take it out of the box to measure it. But I look forward to seeing those results soon, and hopefully it'll show that this cleaning step is effective at improving the fabrication. Other aspects of my intended future research is, first of all, to actually get the photocurrent measurements out of this device once we've produced one that's clean and usable. So this data is actually photocurrent measurement that one of the grad students we work with took on another sample, so I'd like to get similar data from mine. I also hope to make devices with more contacts, because basically the more contacts you have on your flake, the less impact the resistance of the contact material has on your measurements. So making more contacts would enable us to get even better photocurrent measurements. And finally, I'd also like to measure the reflectance of my sample in this mid-IR microscope, which actually my colleague Bailey's about to explain why reflectance data is so important for these measurements, so I'm going to leave that explanation up to her. So in conclusion, MOT2 is an interesting material because of its potential applications to optical detection and power generation, but also because studying it can enable us to learn how the electron wave function evolves in this material and to measure that directly. So I talked briefly about how devices are often fabricated, and I also went into how the methods we use in the Birch lab are different from some of these common methods, and how we can use something as seemingly ordinary as a piece of tape to produce something as extraordinary as these devices. So I talked a bit about the devices that I made this summer and how I'm working to use argon plasma to clean these contacts to make them, to improve them. And finally, I'm looking forward to my future research in the Birch lab on this topic in the fall. So before I go, I'd just like to acknowledge everyone who's helped me in my research, particularly Dr. Ken Birch for inviting me to be a part of his lab, all my Birch lab colleagues, but particularly Gavin Osterhout, Mason Gray, and Dr. Narendra Kumar for being willing to help me, collaborate with me, and answer all my questions, even the annoying ones. I'd like to thank the NSF and the Department of Energy for funding this research, Boston College for hosting this REU, and finally all of my fellow REU students for making this a really great summer. Any questions?
First of all, I'd like to say thank you for your presentation. I definitely learned a lot, and I'm interested in hearing more about your future research. Firstly, I wanted to ask, what is the relative resolution of your gold contacts compared to the size of your molybdenum telluride sample?
So the system that we actually use to write, to shine the UV light on particular areas, has a 1 micron resolution. So even compared to the size of our flakes, which are usually on the order of 10 microns long, we can get a pretty decent resolution of the contacts.
Okay, but what is the relative size? I mean, how much bigger are the contacts compared to the actual?
How much bigger are the contact pads that the contacts go out to? So usually what we have is we have a small contact on the flake, and then it sort of spreads out like a triangle to a millimeter by millimeter pad that we can then wire bond to.
Oh, okay, all right. And additionally, what kind of signal do you expect to see from your results? Do you expect it to be similar to that Gavin was able to derive?
I'm not 100% certain on that, but I think I would expect something similar, as they're both Lyell semi-metals.
Thank you.
So thank you again for giving the talk. It was incredibly informative and engaging. But something I was curious about is you mentioned that MOT has a lot of potential applications. So I was wondering if the air sensitivity could limit those potential applications.
That is quite a fair concern, and I think it also depends on I mean, right now we're mostly concerned about sort of making these prototype devices so we can test, how big is this response at all and what does it look like. So for our concerns, being able to cap it with HBN and to work with it in the glove box during the fabrication process is a pretty good answer to those concerns. As far as what it would look like to, say, scale that up to like something commercial, if that were like possible or reasonable, that's not something I've considered yet, but that would certainly be interesting to look into.
Sorry for like the multiple questions, but did you grow the crystals yourself, or did you like get them from someone else? And if you did grow them yourself, like how did you synthesize them?
We actually received the crystals from one of our collaborators.
Who's your collaborator?
Professor Bertrand Gross, or MIT too?
Kim something, someone Kim.
Oh, okay. Thank you.
I'm just curious, do you have any metric as to how effective the HBN is in protecting the device, especially since you're putting gold and things on top of it? Maybe you have gaps in between them. Just how do you test for air sensitivity?
Well, one of the things we did is we had a device actually in the spring that we left out in air without being capped. And based on, we took IV curves, resistance measurements of each of those. And even this device we had that didn't perfectly work, we fit the linear portion of that graph to try to get an estimate of how big the resistance was, and compared to the device that was left out in air, it was like an order of magnitude difference. So obviously we can tell there was some sort of degradation in the device left out in air.
Do you have any other way to tell if the crystal's okay?
We also do Raman spectroscopy on our crystals, so checking those.
That's a nice secondary check.
Yeah, who would use optics anyway? Okay, if there are no other questions, let's thank Marissa again.